Audio recording lectures for visually impaired students. Modern approach to physical chemistry. BSc Part 2 by S. Kiran. Chapter 7 Electrochemistry. Electrical transport. Electrolytic and metallic conduction. Conductors. The substances through which electricity can pass are known as conductors. On the other hand, the substances through which electricity cannot pass are known as insulators or non-conductors. The conductors are broadly classified into two categories, namely metallic conductors and electrolytes. Metallic conductors. These are the metallic substances which allow the passage of electricity through them without undergoing any chemical change. Some common examples are copper, silver, aluminium, etc. The conduction through which metal is due to the conduction through metal is due to the movement of electrons in them. Beside metals, some minerals and a non-metal graphite also show conduction due to the movement of electrons. They are collectively called electronic conductors. B. Electrolytes. These are the substances which allow the passage of electricity through their molten state or through their aqueous solution and also undergo chemical decomposition. Some common examples of electrolytes are acid, bases, and salts. In this type of conductor, the charge is carried by ions. This type of conduction is referred to as electrolytic conduction. The electrolytes are further classified into categories depending upon their extent of dissociation. These are strong electrolytes and weak electrolytes. Strong electrolytes. The electrolytes, which are almost completely dissociate into ions in aqueous solution, are called strong electrolytes. For example, mineral acid like HCl, etc., base like NaOH, KOH, etc., and salt like NaCl, NH4Cl, etc. Weak electrolytes. The ionize in solution to the smaller extent. In other words, they have low degree of ionization. Their aqueous solution contain ion in equilibrium with dissociated molecules. Some examples are NH4OH, CH3COOH, etc. Non-electrolytes, the substances which do not conduct electricity either in their molten or through their aqueous solution, are called non-electrolytes. Some examples are alcohol, sugar, glucose, etc. Factor affecting electrolytic conduction. In aqueous solution or molten state, the electrolyte splits up into ions. The free movement of ion is responsible for the conduction of electricity. The electrical conductivity of solution therefore be related to the number of ion present in the solution. Some of factor on which electrical conductivity of the solution of electrolytes depend are: first, interionic attraction. These are the attractive interaction between the ions formed by the electrolytes in the solution and are known as solute-solute interaction. Larger the interaction, lesser is the freedom of movement of ions and smaller will be the electrical conductivity. Second, the solvation of ions. These are the attractive interaction between the ions of the electrolyte and molecules of the solvent and are known as solute-solvent interaction. Larger the solute-solvent interaction, larger will be the solvation and lower will be the electrical conductivity. Third, viscosity of solvent. These factors depend upon the attractive interaction between solvent molecules, which is referred as solvent-solvent interaction. Larger the solvent-solvent interaction, larger will be the viscosity and more will be the hindrance to the movement of ions. Hence, low will be the electrical conductivity. Fourth, temperature. As the temperature of electrolytic solution is increased, the effective collision and above factor diminish and the kinetic energy of the ion increases. This results in the increase of electrical conductance of electrolytic solution. The difference between metallic conductor and electrolytic conductor are given. Metallic conductor. Conduction through metal is carried by the movement of electrons. No change in observed in the chemical properties of the conductors. It does not involve any transfer of matter. The resistance of metal is due to obstacle of vibrating kernels of metal atoms. It shows increase in resistance with the increase in temperature. The conductivity of metal is generally high. Electrolytic conductors. Conduction through electrolytes is due to carried charge by movement of ions. It involves chemical change resulting in the decomposition of electrolytes. It involves the transfer of matter as ion. The resistance of the solution of the electrolyte is due to the factor like inter-ionic attraction or viscosity of solvent, etc. They show decrease in resistance with the increase in temperature. The conductivity of electrolytic solution is generally low. Some basic concepts. First, Ohm's law. This law is obeyed by both the metallic as well as electrolytic conductors. It states that the current flowing through a conductor is directly proportional to the potential difference across it, that is, I is directly proportional to V, where I is the current strength and V is the potential difference applied across the conductor. I is expressed is in ampere, V in volt, and R is expressed in ohm. Resistance R of any conductor is the obstruction to the flow of current. It is directly proportional to length L of the conductor and inversely proportional to its area A of cross section. R is equal to rho L by A, where rho is the constant of proportionality and is known as specific resistance or resistivity. Number 2. Conductance. Conductance is a measure of ease with which current flow through the conductor. It is defined as the reciprocal of the resistance and is denoted by C. Unit of conductance are ohm, inverse and mho. SI unit of electrical conductance are Siemens. Specific conductance, equivalent conductance and molar conductance. Specific conductance. It is the reciprocal of specific resistance and is also called conductivity. It is denoted by a Greek letter kappa K. It may be defined as the conductance of a solution of length and having 1 square centimeter as the area of cross section. In other words, conductivity is the conductance of 1 centimeter cube of a solution of any electrolyte. Kappa is equal to 1 divided by rho. Unit The unit of specific conductance are ohm inverse centimeter inverse, Simon centimeter inverse, or ohm inverse centimeter inverse. In SI unit, the area of cross section is expressed in centimeter square and length is expressed in meter. Then the unit of conductivity are Simon meter inverse, ohm inverse meter inverse. Equivalent conductance. The electrolytic conductance of an electrolytic solution not only depend on temperature but also varies with the concentration of the solution. It is due to the fact that conductivity of solution is attributed to the presence of ions. The number of ions in 1 centimeter cube of the solution changes with the concentration. In order to compare the conductivity of different electrolytes, we consider the solution of equivalent concentration, that is solution which produce ions carrying the same total charge of electricity. For example, 1 gram equivalent of different electrolytes produce ions carrying same total charge of electricity. Thus, we compare the conductivities of electrolytes in terms of equivalent conductance. Equivalent conductance is defined as the conductance of a solution containing 1 gram equivalent of electrolytes such as that the entire solution is placed between two electrodes 1 centimeter apart. It is denoted by the symbol lambda equivalent. Relationship between specific conductance kappa and equivalent conductance lambda equivalent. To derive relationship between kappa and lambda equivalent, consider volume centimeter cube of solution containing 1 gram equivalent of electrolyte placed between two electrodes 1 centimeter apart. Let the conductance of solution X, as the solution contains 1 gram equivalent of the electrolyte. Therefore, the measured conductance also represents the equivalent conductance. Hence, lambda equivalent is equal to X. As the volume of solution is V centimeter cube, therefore the number of centimeter cube in V volume will be equal to V. The conductivity K is the conductance of 1 centimeter cube of the solution, that is KV, where V refers to the volume containing 1 gram equivalent of electrolyte. If C is the concentration of the solution in gram equivalent per liter, that is normality of the solution, then the volume of solution containing 1 gram equivalent of electrolyte can be calculated as follows. C gram equivalent of electrolytes are represented in 1000 centimeter cube of solution. 1 gram equivalent of electrolyte is present in is equal to 1000 divided by C centimeter cube of solution. Thus, lambda equivalent will be equal to kappa into 1000 divided by C, or kappa into 1000 divided by N, where N is the normality of the solution. Unit. The unit of equivalent conductivity are ohm inverse centimeter square equivalent inverse, or ohm inverse centimeter square equivalent inverse, or Simon centimeter square equivalent inverse. Molar Molar conductance. The recent trend is to describe electrolytic conductance in terms of molar conductance. Molar conductance is defined as the conductance of the solution containing 1 gram mole of the electrolyte in that their solution is placed between two parallel electrodes 1 centimeter apart, denoted by lambda m. Molar conductance is related to conductivity of specific conductance kappa. Del m is equal to K into 1000 divided by m, where m is the molarity of solution. Unit of molar conductance are Simon centimeter square mole inverse, or ohm inverse centimeter square mole inverse. In SI unit, molar conductance is expressed as Simon meter square mole inverse. Experimental measure of conductance, specific conductance and equivalent conductance. First, measurement of conductance. The conductance of a solution is reciprocal of resistance. Therefore, if resistance of solution is known, its conductance can be calculated. The resistance of solution is measured with the help of Wheat-Stonebridge method, the arrangement of which has shown in figure. One arm of the bridge is attached to the conductivity cell containing the solution. The conductivity cell is Pyrex glass and is fitted with platinum electrode. These are plated black with finely divided platinum. The cell is placed in to keep the temperature constant. It is because the conductance changes with temperature. The bridge is connected to a source of alternating current. The alternating current at a frequency of 1500 to 3000 CPS is employed. It may be noted that the direct current is not used here because it causes electrolysis, as a result of which the concentration and hence the conductance of solution changes. When the current flow through the circuit, the resistance R1, R2 and R3 are so adjusted that a null point is obtained. The null point is indicated by the detector D at this point. At this point, R1 divided by R2 will be equal to R3 divided by R4. Knowing the value of R1, R3, R4, the resistance of electrolytic solution R2 is calculated. R2 is the resistance of electrolytic solution, that is equal to R1, R4 divided by R3. Number 2. Calculation of conductivity. The conductivity K is reciprocal of resistivity rho. K is equal to 1 divided by rho is equal to C L by A. Here L is the distance of separation of two electrodes and A is the area of cross section of the electrode. The quantity L divided by A is called cell constant. The cell constant is expressed in unit centimeter inverse. Hence, the conductivity is equal to cell constant divided by R. Determination of cell constant. The cell constant is generally not calculated with the help of values of L, A, and A because these are difficult to measure for a given cell. It is determined measuring the conductance of standard solution of KCl whose conductivity is known at a different concentration and temperature as given in table. Number 4. Calculation of equivalent conductance. Equivalent conductance lambda equivalent and specific conductance kappa are related as conductivity is equal to cell constant divided by R. Lambda equivalent is equal to K into 100 divided by C equivalent, where C equivalent is the normality of solution, that is the concentration of solution in gram equivalent per liter. Thus, knowing the normality of the solution and specific conductance K, the equivalent conductance lambda equivalent can be calculated. Variation of specific conductance and molar conductance with dilution. The conductivity or specific conductance decreases on dilution for both strong and weak electrolyte. Conductivity is the conductance of unit volume 1 cm cube of the electrolyte, which increase in dilution the number of ion per unit volume of the solution decreases. Consequently, the conductivity of the solution also decreases with dilution. Number 2. Variation of molar conductance with dilution. Molar conductivity del M of both strong and weak electrolyte increases on dilution. Molar conductance and specific conductance are related as del M is equal to 1000 into K divided by C. Specific conductance K decrease with dilution, but this decrease is overcompensated by increase in the value of 1 divided by C on dilution. As a result, del M increase as the solution is diluted. The variation of molar conductivity on dilution for strong and weak electrolyte shows different trend and that can be seen from figure 3. The graph showing variation of del M versus root C for KCl. A strong electrolyte and CH3COOH, which is a weak electrolyte, is shown in figure. The graph shows following trends. First, for strong electrolyte, the variation of del M is linear in dilute solution. Del M attain limiting value which dilution approaches infinite, that is when concentration approaches zero. This value of molar conductivity when the concentration approaches zero is known as molar conductivity at infinite dilution, denoted by del M infinite. For strong electrolyte, the value of molar conductivity at infinite dilution is determined from the graph by extrapolating it to zero concentration. Strong electrolytes are almost completely ionized in solution. However, in the concentrated solution of strong electrolyte, there are strong inter-ionic forces. With dilution, the ion became far apart and inter-ionic forces decreases. As a result, molar conductivity increases with dilution. The mathematical relationship between del M and del M infinite for strong electrolyte was given by D by Huckel and Onsager and is given as del M is equal to del M infinite minus B under the root C, where B is a constant depending upon the type of electrolyte, the nature of the solvent, and the temperature. This equation is called D by Huckel-Onsager equation. Here, del M is the molar conductivity at concentration C and del M infinite is the molar conductivity at infinite dilution. It is evident that as C approaches 0, del M will be equal to del M infinite. In case of weak electrolyte like acetic acid, the degree of dissociation increases, thereby increasing the number of ions in the solution. However, there is no indication putting value even when the concentration approaches 0. The limiting value cannot be extrapolated. There is an indirect method for obtaining molar conductance at the dilution for weak electrolyte, which is based on Collard's law. Assuming that increase in molar conductance on dilution is only due to increase in ion of dissociation of electrolyte, it is evident that when limiting value of molar conductance approaches the degree of dissociation is unity. Thus, the degree of dissociation alpha is given by alpha is equal to del m divided by del m infinite. Arrhenius theory of electrolyte dissociation. According to Arrhenius theory of electrolytic dissociation, an equilibrium exists between the undissociated molecule AB and its ions A positive and B negative that are formed by ionization of electrolyte. Thus, AB is equal to A plus B minus. The equilibrium constant for this equilibrium is written as K is equal to A positive B negative divided by AB. Let A be the degree of dissociation of electrolyte and C be the initial concentration of weak electrolyte AB. Then at equilibrium, the molar concentration of AB, A positive and B negative are A positive is equal to B negative is equal to C alpha. AB is equal to C1 minus alpha. Hence, K is equal to C alpha into C alpha divided by C1 minus alpha is equal to C alpha square 1 minus alpha. Arrhenius suggested that the degree of dissociation alpha of an electrolyte is given as alpha is equal to del M divided by del M naught, where del M is the molar conductance at a given concentration C and lambda naught is molar conductance at infinite dilution. Substitution equation we get K is equal to C lambda square divided by lambda naught minus lambda. Limitation of Arrhenius theory. Arrhenius theory does not take into consideration the interionic interaction and is only applicable to the dissociation of weak electrolytes. D. by Huckel theory. In 1923, D. by and Huckel and in 1926, Onsagar put forward the modern theory of electrolytes, in which account is taken of the electrostatic force between the ions. Migration of ions. The electrolyte dissociate in solution to form positive and negative ion. When this is conducted through the solution of electrolyte, the ion migrate toward the opposite charge electrode. This movement of ion toward a positively charged electron is called migration of ions. The phenomenon of migration of ion can be shown by the following experiment. The apparatus consists of a U-tube made of hard glass. The lower portion is filled with the aqueous solution of 5% agar and a small amount of copper dichromate. Since the salt is not available as such, a mixture of CuSO4 and K2Cr2O7 is used. It is green in color and is set into jelly in agar on cooling. The surface of the green jelly is marked by placing a small amount of powdered charcoal in both the limbs of the U-tube and layer of KMNO3 solution in agar solution agar is placed, which also set into jelly on cooling. The electrode are immersed into KNO3 solution in pure water at the top of the second layer. When current is passed, the blue Cu dipositive ion start rising through the jelly in the cathodic compartment, while orange Cr2O7 dye negative ion in the anodic compartment of U2. After a while, the two types of ions start migrating with well-defined boundaries. The function of jelly is to avoid mixing of solution due to diffusion. Relative speed of ion and change in concentration. Hittov's theoretical device. We have already considered that ion move to the positively charged electrodes under the influence of electric current, but the speed of cation migrating toward the cathode and those of anion migrating toward the anode are not necessarily the same. However, the speed of a cation moving away from anode will be proportional to the fall of concentration of these at the anode. Similarly, the speed of an anion moving away from the cathode will be proportional to fall of concentration of anion around the cathode. Hitov studies such changes and experimentally and give a general rule known as Hittov's rule. It states that the loss of concentration around any electrode is proportional to speed of ion moving from it. Hitov rule may be illustrated by Hittov's theoretical devices as follows. In figure A is in figure A is anode and C is cathode. A dash and B dash are two imaginary planes which divide the cell into three compartments. The anode compartment, in the middle compartment, the cathode compartment. The sign positive represents a cation and sign negative represents an anion. Before electrolysis, let there be 15 pair of cell having 5 ion pair in each of three compartments. Now consider the following case. Case 1. When only cation move. When we see two cation move toward the cathode, we get position 2. But the number of cation and anion discharged is same, that is 2. The concentration in the cathode compartment, however, has not changed while in the anode's compartment it has fallen by 2 ion pair. Similarly, if only two anions move toward cathode, there is fall in concentration in the cathodic compartment by 2 ion pairs. Case 2. When cation and anion move at some rate. When two cation and two anion move toward the opposite electrode, we get the condition shown in third. The number of discharged anion and cation in is same, that is 4. The concentration of both the anode compartment and the cathode compartment has fallen to same extent. Case 3. When the cation move at twice the speed of anions. In this case, when two cations have moved to the cathode compartment, only one passes into the anode compartment because the speed of anion is half that of cation. This is shown in position 4. The total number of discharged anion and cation is again the same, that is 3. Although the concentration in the cathode compartment has fallen by 1 ion pair, the concentration in the anode compartment decreases by 2 ion pair. Following conclusions are made from above illustration. First, ions are always discharged in equal number on opposite electrode irrespective of the speed of ions. Number 2, change in concentration around the electrode is caused due to the difference in the speed of anion and cation. Loss in concentration around any electrode is proportional to speed of ion moving away from it. This is Hittov's rule. We can write the expression fall around anode divided by fall around cathode is equal to speed of cation divided by speed of anion is equal to UA divided by UC, where UA and UC is the speed of cation and anion respectively. In deriving the above relation, an important assumption has been made, namely the discharged ion do not react with the material of electrode. However, in many cases they combine with material of electrodes. This results in an increase in concentration around such an electrode instead of a decrease. Case 4. When electrodes are attackable. Let us study the electrolysis of silver nitrate using silver electrode in a silver voltmeter. We find that instead of fall in concentration of AgNO3 around silver nitrate, an increase in concentration is observed. This is due to the fact that every NO3 negative ion that reaches the anode reacts with Ag positive ion of the electrode to form AgNO3. As a result, there is increase in the concentration in the anodic compartment. With silver electrode, various possibilities are shown in figure. It-offs devices when the electrodes are attacked. In figure 8. It is seen that in every case there is always an increase in the anodic compartment. This increase in concentration takes place even when the Ag positive ion migrate from anodic to the cathodic compartment. It is easy to find the increase in concentration by putting a silver or a copper voltmeter called coulometer in series. Suppose a number of gram equivalent of copper and Ag deposit in the coulometer is X. This would give the total current passed or increase in concentration around the anode if no silver ion has migrated toward the cathode. The difference of the total increase and the actual increase around a anode give the fall in concentration around the anode due to migration of Ag positive ion. It is obvious that a gram equivalent would have been the increase in the concentration of anodic compartment if no Ag positive ion has migrated from this compartment, but the actual increase is due to the migration of Ag positive ion. Suppose the actual fall increase in the concentration of Ag in the anodic compartment is B gram equivalent. Thus, fall in concentration in the anodic compartment due to migration of Ag positive ion is equal to A minus B gram equivalent. Also, it may be seen from figure 8 that fall in concentration around cathode is equal to increase in concentration around anode is equal to B gram equivalent. Hence, speed of Ag positive ion divided by speed of NO3 negative ion is equal to A minus B divided by B.